Hi, I'm Russell Leidig. I'm going to show you how to use Orthohack from TigerSpike to generate an 8x8 real-valued discrete cosine transform and its inverse. This particular transform is used in the JPEG image processing algorithm. So first of all, if you look at the files, you'll notice this one here, which copying, which describes all the licensing terms of the intellectual property. So without further ado, if we look at build.h, you can see that this is build number 93, which was released at the first blog entry of orthohack.blogspot.com. Please use that for the purposes of this training. Then at the end of the file, you'll see the stuff about pthreads. This enables multiprocessor support. This should be fine in any modern Linux version, but if you have any problems, you might want to delete these two lines. Okay, the first thing that we need to do, just to be paranoid, is do a make clean like this, which deletes a bunch of files. And by the way, if you're unable to execute that, you can always try /bin/sh space /makeclean.sh. Okay. The next thing that we need to do is we need to make the preprocessor. But before we make the preprocessor, I want to show you kind of what it does. We're going to build the inverse discrete cosine transform first. So if I switch into this demo directory /IDCT 8x8, you can see all these 63 files. These are 512 bytes each, which is 64 samples times 64-bit floating point values, describing all of the orthobasis vectors in the transform. And here, in fact, is a reference output for the preprocessor. If you compare to that reference output, you may find differences if you have a slightly different floating point implementation than I happen to be using on x86 64 under Ubuntu 12 something. Okay, so let's go ahead and make the preprocessor. I put 64, you might have to put 32. So run that, and you can put /bin/sh on that as well if you need to. So let's go ahead and run it. Okay, and change back into the inverse discrete cosine transform directory, and you can see, in fact, there is an IDCT .ohk file. So the transform has emitted all of this wonderful information. We can diff it, and it turns out to be the same, which is good. But let's look back here a second at what the preprocessor actually did. You can see that it's discovering all these binomials with various populations. I discussed this in a previous video about hierarchical ratio analysis. So you'll notice that these populations are really elegant: 32, 16, 16, 16, 8, 4, 4, 4, 4, 2. So that suggests that we've perhaps found an optimal transform, or close to optimal. I don't know. It doesn't prove anything, but when you see symmetry like that, it's certainly suggestive that something good is happening. So okay, now we need to make the post processor. So I'm going to do that. Make Linux 64 post. And let's just run it. This generates all the information that's actually needed for the transform. The OHK file, by the way, is not actually needed for the productized transform, but this include file is. And this is a very platform-independent file of basically data tables for fixed point, custom fixed point, and floating point transforms. And then it's got a bunch of instructions on how to do the transform that are encoded as bit codes, essentially. But we need to copy that output. We need to redirect that output to a file called orthohack.h. Sorry, that's kind of awkward, but that's the way it is for now. Yes, all of this needs a graphical user interface. I realize that, but I don't have any time at the moment. So for the purpose of the demo, I'd like you to copy that to demo /IDCT 8x8 underscore orthohack. You can see there's a reference for that already, orthohack.h. And in fact, let's go ahead and compare that to the reference file that's been supplied to you. Now, yours might differ because of floating point differences, but that won't be a problem because the topology should still be the same, and we're going to test the topology in a bit. Okay, so that actually compares. That's good. So let's go ahead and make the literalizer, which dumps all of the instructions in the entire transform, literally with no loop instructions. And let's run the literalizer. Okay, that looks good. It prints a bunch of A's, B's, C's, and D's, and the A's and B's have scrolled off. But these are just basically multiply, add, and multiply, subtract operations. And I'll tell you about that in a future video. Let's redirect that to demo IDCT 8x8 ortho literal, and you can see we've got a reference for that. And that is a C file because it is actual code. And then let's go ahead and diff that. And no matter what kind of floating point you're using, in all probability, this should diff correctly. So if it doesn't, something is quite possibly wrong. Compare that to the reference, and there's no differences. So that looks good. Okay, now we have to build DCT. We just built IDCT. So go into config.h, change the path name. This is where the database, the orthobasis database is. Delete that I, so it's DCT. Delete these i's in the file name. So DCT/DCT 8x8ohk. Yes, write the config file, and start over. Let's rebuild the preprocessor. And run the preprocessor. And you could diff it, but I'm not going to take time to do that right now. Make the postprocessor. Run the postprocessor. No errors. OK. Redirect to orthohack.h. OK. And make the literalizer. And run the literalizer. Just run it. OK. So we can redirect to demo/DCT 8x8 ortho literal. Okay, and then let's go ahead and diff that with the reference version. By 8 ortho literal reference. No differences. So the transform topology is the same. Highly encouraging. And I forgot, we also have to copy orthohack.h, in this case, to DCT 8x8 orthohack, not the reference, don't overwrite it, .h. Okay, now we have built everything we need for the demo. So let's actually build the demo itself. Linux 64 demo build, demo.sh. And it tries to delete the previous executables. They aren't there, so it can't do it. So let's go ahead and run it. Let's run the DCT first. DCT 8x8 demo. And a bunch of junk comes out. So let me tell you what this is doing. It's just taking this input up here. You see this input matrix X. Okay, this is an 8x8 matrix. And it's printed out in the same really awkward MATLAB/GNU Octave format. And so this is column 1, this is column 2, column 3, blah, blah, blah. And then it takes the DCT, and it uses the literal transform. That's that big listing of A, B, C, and D multiply add operations, the topology stream we just captured. And it executes that, and it comes out with these values. And it also uses a generic floating point transform based on all the values encoded in orthohack.h. And it does that transform and comes out with the same numbers. And it does it in a by 8 transforms at the same time, or actually, to be more accurate, tightly pipelined, and it comes out to be the same thing. It also does it in fixed point, and you'll notice a bit of lost precision here. This is 32.32 fixed point, excuse me, in by 1 and by 8 geometries. And by 8, of course, could eventually be converted to SIMD and be truly parallel, but I haven't done that. And then custom fixed point, which is 32 bits with a relocatable binary point. It does it in by 1 and by 8, and you'll see a little bit more error injected there. But let's go ahead and see if these values are right. So, okay, how do we do that? Well, let's take something that's as close to exactly right as possible, which would be the floating point. We do literal floating point. Let's just take this value here at random, 5 point something times 10 to the minus 2. Copy that. Let's look at the reference output. So if we cd to MATLAB, there's a file in here which came out of MATLAB when MATLAB did its own DCT. This is the demo output file. And if we grep that file, I'm going to paste for this, we may or may not find it. And indeed, we don't find it because MATLAB is using a slightly different transform. So let's delete some of the terminating digits and see if we find it. Oh, there it is. What do you know? So within, some tiny, tiny difference, we've generated exactly the same output that MATLAB has. And I'm not going to do all 64 values, but you can do that yourself, and you can see that, in fact, this is a quite accurate transform. Okay, and then the only other thing we need to do is worry about the IDCT demo. We can do the same thing here. It's the same format of output. I'm not going to describe this whole thing again. But let's go back to, I don't know, let's say floating point by 8. And we're going to randomly select this value. We don't need to worry about the minus sign. And we're going to go ahead and go back to MATLAB. And we're going to grep for that. Let's delete this previous value. Paste it in the new value. Oh, he has it exactly. How cool. So this thing's really precise. That's good. Anyway, I will tell you in subsequent videos about all the details of this and how to customize it for what you need it to do. So stay tuned.